like I told you, right, MinIO is just is a web server. And the way it works is, if we see, like to contrast with other traditional systems, when early on I meant that every other object storage took a textbook theory. What they did, whether it's a distributed database or a data store or a file system or an object store, they always saw they are all one and the same problem. Essentially, you need to do consensus, some kind of distributed locking, you need to do data replication or erasure code. These are all the same old theories. You hire the same engineers. You don't go to new places if you follow the well-laid roads already, right? So with the way we saw this problem was, none of this is true. It's just a web server, and it's a single layer architecture. And it is also strictly consistent and atomic, right? When every operation that comes into MinIO, all those benchmark numbers that we are showing, it's inline erasure code, inline bitrot, inline like encryption. When the application gets the response back, it is done. And you crash MinIO in the middle of the application, you're not losing any data, right? Every single operation is atomically committed. And if we are losing data at this scale, even 0.1% of our users losing data, you will know, right? That's what allowed us to grow really fast. Now, how does it come into the architecture? So how is it actually doing it? Say, if you look at this command line, right? MinIO server, and then it's just an endpoint, right? And the endpoint, it actually uses a simple wildcard pattern. So essentially what it's saying is there are 32 hosts and 32 drives on each one of them. So it's a command line that tells MinIO there are totally 1024 drives spread across 32 servers. What do? You take the MinIO binary, that's like the static binary, copy to all the 32 nodes, and you type the same exact command on each one of those nodes. Now they all come up. Every node is equal. There is no metadata, name node or anything else, lock server, nothing. Every server has all the same capabilities, and they come up. How do they know each other? Because the command line says so. So they all see each other, and they become a distributed object storage. And by default, you can lose, depending on, say, if you do a 12, so the default is 8 data, 8 parity, which means that every object is striped across 16 drives, and you can lose as much as 8 drives, and your data is always available. Now, the data is also, the 16 drives, it doesn't pick 16 drives from one node. Every object is striped horizontally, so you can lose 8 nodes, and your data is still readable. For writing, you need n by 2 plus 1. So as long as 9 nodes are online, your data, that object is readable. Now, in environments that are attended, they actually do 12 data 4 parity. So anytime you can lose 4 nodes and you can read and write. But this setup, the default, why did we do 8 data 8 parity? Many of the development and many of the developers actually put us on the environment, and then they start growing fast. They don't want to go back and do ops. People lose money actually attending ops, going there, typing the command, replacing drives. You deploy and you forget it. Eventually, you decommission the cluster because you have too many failures. When you have 40% of the drives and nodes failed, it's time to decommission the cluster. That's how the default setup is. Essentially, you copy the MinIO binary to 32 nodes, type the same exact command, and they all come up. Every node has a single process, and it's heavily threaded. In fact, it's lightweight threads called Go routines, and it becomes aggressively parallel, lightweight system. Now, if you want multiple tenants, you literally start another MinIO server on the same machines, even sharing the same set of drives, and just run on a different board. In real world, more and more I see people don't type these commands. They actually just do helm install MinIO, and in a single command, it just spins up MinIO on a distributed cluster. Kubernetes makes it just easier. They just don't really do these things by hand. But when they are starting, they want to understand things. This is how you do it. Even if bare metal, doing things by hand, it is that simple. Every node is just one MinIO server, and they all see each other. The request can come to any one of them. In fact, in the real world, when you download even a single object or upload a single object, they are often broken into parts. The SDKs themselves do this. They actually they do range get or a multi-part upload. By the time it hits the server, even a single object is sharded across. The requests are sharded across all the nodes, and every node is contributing. By being strictly consistent and coherent, MinIO knows how to deal with this atomically. And let's go into more details, right? How do I scale, right? How do you build very large systems? Nowadays, actually, 10 petabytes is becoming like the new 100 TB. 10 petabyte community deployments we quite often see they are in the range of like 5 to 10 petabytes, and some of them are now looking at 100 petabytes. And what is the scaling model in MinIO? Sure, you can bring all your 100 petabyte. Like say on average we see 6 petabytes per rack. When you go to 10 petabyte plus, they actually take a JBOD, a dense JBOD model, essentially 1 petabyte or 1 to 1.5 petabyte per server. That's a dense 4U JBOD, and then they put like 6 JBODs per rack, and then you keep adding the racks. And as you add the racks, the scaling model is they always think in terms of scalable unit. What is a scalable unit? Scalable unit is simply a failure domain that you can tolerate. The best way to build a very large infrastructure is don't build a very large infrastructure. You build in pods, like each pod is a scalable unit. So failure should never leak beyond. If any failure happens within that failure domain, everything is well understood. You know exactly how to treat. If you want to service the cluster, you want to push updates, everything is well understood because it's a failure domain. And to keep building large, you simply keep adding scalable units. Every time you expand, you add new racks. Those racks are going to be different in configuration because the drives got cheaper, the newer processors came, so it's going to go heterogeneous whether you like it or not. But every time you deploy a rack or a set of racks, in many cases I see they actually go for a single rack as a failure domain. That's one scalable unit. They keep adding one rack at a time at large scale. And the financial institutions actually want 4 rack or a 6 rack in one failure domain because they want total rack failure. So the erasure code is horizontal across racks. They just make sure that the top of the rack switch has fat tree configuration. And this model, you just keep scaling. And now, what's your confidence level when you go to 100 petabyte or an exabyte? For me, it's very, very simple because if it worked well on one scalable unit, they are literally share nothing, separate clusters. Running 100 separate clusters of MinIO, that's pretty much the design underneath. And this allows us to actually optimize the right things. No algorithms are actually good at small scale and very large scale. And building a giant basket where you can put all the eggs, the engineering principles are very different. It just doesn't work. This is how Facebook to Apple to Google, everybody built their large infrastructure, right? This is very early on.
So when you're putting an object into this configuration here, where does it go?
Yeah, so let's trace the path, right? So the scalable unit. So let's take say this is each one.
Something like
that. Each one is a scalable unit. MinIO's terminology is called zone. Now you have multi racks, multi data center. Now I want to upload an object into a bucket, say my bucket, right? My object I want to upload to my bucket. The application actually always, from any application, my bucket, they look up a DNS and then the IP gets resolved into which cluster has that bucket. The bucket actually can span even across all the clusters, but say, so let's take in a simple case, right? So this bucket came in this data center. Now within this data center, now in terms of uploading, it finds which rack has the most free space. So each set of racks, say each one is a scalable unit. So you started with this set of racks and then added this later. Now maybe this has more free space. When you upload, it finds which zone has the most free space and places the object. So when you get it, it actually the DNS resolves to the cluster that has the bucket, and within that cluster, every node is equally capable of retrieving the object back to you. Most often, what happens, your request gets broken down into parallel block read, and they go to all the nodes or subset of the nodes in the rack. Each one of them is just giving you the objects. So it's really a simple model by then.
So you're talking about a very complex configuration with zones and everything. Do you have a user interface, a dashboard where I can see what happens? Because
yes.
enterprises,
Yeah.
They are not all,
Yes.
Linux nerds.
We will show you a demo in the end, like how easy it is for the enterprise to deal with this. In fact, this is where Kubernetes becomes really invaluable for the enterprise. It's actually, MinIO is the simplest component in their stack most of the time, because there are application components and other database and everything else that is also scaling. So from MinIO's point of view, they simply look at it as set of servers. And the way in fact, what happens almost always is like they want Kubernetes API. They also have MC admin command that tells you exactly what's going on. Even hey, this application is buggy. Like MinIO has a tool called trace, which is like Solaris dtrace type. Right? It can tell you that this problem is actually your application problem because it uses old buggy Boto package or something like that, right? Or it's MinIO's bug, or it's a bad drive. From a supportability point of view, we'll talk more about that later. But from that to even managing the large installation is literally from a Kubernetes point of view, it's a single YAML file. You describe the setup, deploy it, and done. You want to add a new cluster, you simply edit that YAML file. They are doing this in minutes. That fully it's automated. And the thing is, you can do this when the system is in production and live. You want to upgrade, the update itself is like seconds, right? It's really Kubernetes taking time. MinIO's update is like in milliseconds, being lightweight and by being stateless, it's like restarting a web server.
So a bucket in this case is across the cluster. Effectively, anywhere in the cluster can access the data in that bucket.
Yes. So the bucket is across the clusters. It can actually span across zones too, and then different tenants also can coexist. But generally, you don't want a bucket to be spanning across even multiple data centers. Amazon doesn't do that because it causes unevenness.
Yeah.
Yes. So this one. As they scale, one of the important requirements that customers started asking is, how do I build multi-data center, but then I want my data center like entirely, if they die, I want the remote data centers to be in sync and not lose any data. Here is where like the traditional, even any of these backup tools or data migration tools are slow. They don't even know what changed. Right? MinIO, we know exactly what's changing inside the system. In fact, MinIO has a capability called Lambda Compute notification. This MC mirror, while it looks deceptively simple like rsync tool, underneath is actually a continuous replication code that subscribes to the Lambda notifications. As and when any objects are changing in one data center, it immediately keeps the remote data center in sync. If your WAN link is down for some time, it will eventually catch up. But as long as you have sufficient bandwidth, every change that you are doing, as soon as it happens, its remote site is in sync. And the remote site could also be Amazon S3 or even multiple MinIO sites, and it can keep them in sync.
And this is probably, I'm sure it's there. There's a process for failing back?
Yeah, you can actually, the MC mirror, you can, so if you are making change, so that side, if the mirror is basically to keep it in sync. If you made change here, and then it just brings it back in sync.
Okay.
Yeah. The MC mirror also has a MMR, multi-site, multi-master replication. In that, you can do like multi-site cross-configuration, and it keeps them in sync. Then I think we can skip this for now, but like just to get the high-level point that internally, like where is the simplicity coming from, right? MinIO's data objects are simply broken into parts, and the parts are written across multiple drives, and the drives are chosen across multiple machines. The data path, if you see my data, my bucket, my object, if you go to the backend, the JBOD, each mount point, you'll actually see the same object name, and the object parts are simply written as part 1, part 2, part 3. This is where that we know that it's so ridiculously simple for us to even reconstruct. You brought just few drives back after your data center crashed and burned. We can actually look at it and manually even reconstruct. It's because of the simplicity of the backend that we are able to handle like without any data loss. And you can see that how even the JSON file, you can see how it basically uses like say Reed-Solomon Vandermonde erasure code, and it uses in this Blake to be hashing. The features while they are also pretty sophisticated, written in like even assembly language, it's SIMD acceleration, but from a web server point of view, there's a JSON file, and then there are parts. When the request comes to any one of the server, object names, it simply looks up the backend. It knows that's how every node knows where exactly the object is without a database. If you got to any one of the Excel JSON file, you know exactly how to reconstruct that object, and every object is independently erasure coded, independently bitrot encrypted. And
how's the object ID get translated into, the 4 parts, stuff like that? So it must be some sort of I would hate to say a database, but it's not a database. It's sort of a structure.
Yeah.
The metadata that's shared across all the nodes in the cluster, right? Because they all have access to all the objects.
So every node, in a traditional sense, you look up a database, right? Because there is no database here, how do you get to that object?
Yeah.
So you are now looking for my object, my bucket. DNS gets you to the whichever clusters have that
This
bucket.
information.
Yeah. So now within that cluster, any one of the node you go to, they know exactly. Like how do you know this object is in which set of drives? Within every cluster is a static configuration. So if there are 1024 drives, if you do a hash mod on the object name prefix path, you got a unique handle, right? So now that is the index into. So okay, 65 and the next 15 drives are exactly where your objects are. That particular object is now any one of those drives. If you get to that Excel JSON, you know how to reconstruct that object. It may be using. In fact, the new version we use Blake to P highway hash. It knows, okay, this object, use Blake to P bitrot check. Things like that. It's really a simple design. You can now see MinIO the logic in MinIO is not like a S3 gateway, then you have a metadata database, log server and consensus. You have a virtual file system talking to a remote RBD like block device. None of that complexity. Any web server gets a request, it's a static logic, and you know exactly how to read the object, deconstruct and send the data back. It's really that simple.
How does that hash manage when you extend the cluster then?
So every zone is static, and it's by design because we actually don't want people to be like, every time when you add, rebalancing is the worst thing you can do today because it just takes enormous amount of time and bandwidth, right? The network bandwidth actually. So every zone is static. Now when you want to keep on adding, the elasticity comes from adding zones. You keep adding zones because every zone is static, there is the metadata, the hash namespace doesn't collapse.
Doesn't it create a performance inconsistency, over time? So you have faster and faster node, or maybe you become, a little bit greedy and you want to buy cheaper nodes.
Yes.
So your cluster, and then it's a problem with high performance, applications. So
yeah.
counterintuitive, I mean.
No, you're right? So now it's heterogeneous is something you cannot avoid eventually, right? What we generally find is that these are operational problems as you scale you run into, and it is very much our responsibility to take care. So this is where we actually tell within zone, when you are buying a set of nodes, don't get different configuration because it was on a sale or something. When you buy a rack, let all the nodes be same. It's not, MinIO doesn't force it. You can actually bring even different architecture into the cluster, but from operational point of view, you don't want like this, say 32 nodes in a rack. Some nodes are big denser and some nodes are not denser. That causes unpredictability because those 4 nodes are more special because if they die, they take down a larger amount of namespace, right? So they are homogeneous now within a zone, but as you add, they are heterogeneous. So within an object, within you are always getting consistent performance. Now, what we generally find when they add even new racks, they are always bottlenecked on the network in MinIO's case. On hard drives, we find that when you put like 96 drives in a chassis, even beyond 24 drives, we find that 10 gigabit is a bottleneck for 12 drives. You at least start with 25 gigabit for hard drives or go to 50 or 100. The cost delta is not that much. For NVMe, absolutely start with 100. 100 is what you will find as a bottleneck. So we find that almost always we are not CPU bound. The drives are faster. Network is often the choking point. So when you keep adding zones, we don't see this problem because they are all pretty much choking on the network. So maybe 4 node, maybe 16 node, but then the MinIO knows which zone where the free space is, but within they are all pretty much giving similar performance.
Go back to where, is the object split up into 4 data portions and 1 parity, or something like that, 4 plus 2, whatever the number was?
Yeah.
I'm just trying to, so this is the case where it's 4 plus 1, right?
This is actually 2 plus 2, 2 data, 2 parity. You can't see it's in small font. In this case, it's just to explain the concept. So an object is broken into 4 parts. In fact, like the large objects are broken into mod 4.
And this is just showing 1 part of those 4 parts?
So this is just showing the Excel JSON in one of the parts says, because every Excel JSON is self-contained to describe the whole object. So it says, hey, this part is actually the second part. Each object, it says that the objects are broken in this order. Every object is independently erasure coded, and they're shuffled also. You don't always want the last 2 nodes to be parity nodes. So this is the order that says, actually, in this case, first and last node has data. The second and third node has the parity. So MinIO knows, in this case, as long as these 2 drives are available, it actually simply has to read and concatenate.
It just hashes the object ID to determine which node to go out to?
We don't even
disk?
The in-memory. Yeah, stateless and in-memory. It's deterministic hashing. So you just know which disk, because a zone is static. It's really a hash mod logic, right? And you know exactly which set of drives.
So I'm concerned is that every one of those parts are listed as part.1. Are they really part 2, part 3, and part 4?
Yes, for this demo, it's a small object. So when you can go up to 10,000 parts based on S3 standard. Each part, so this is what this says is, part 1 itself is erasure coded. So this part and this part are data part, this part and this part are parity
Shouldn't
part.
they be listed like part.2 and part.3 and part.4?
If you upload a large object, you will start seeing that part.1, part.2, part.3, and each part.
Oh, I see.
Yeah, this is basically
What's the generation of the part?
Exactly. Each part, this is one part. Literally, if you download a small object, it fits in single part. That one part got erasure coded, and then basically this is a part that got sharded across 4 drives. In a real world, like when each part is like 16 drives and sharded horizontally.
I'm good.
Okay.
Can I change every erasure coding schema that I want, or it's fixed? Because at the very beginning was 4 plus 4 fixed.
Yeah. So the default is n by 2, right? So they did 8 data and 8 parity. But in most enterprise environments, like you can at least go once in 3 months, once in 6 months, like recoup the dead drives, and you just put a new drive and it starts self-healing on its own. If that's the case, you absolutely can go for 12 data and 4 parity. In fact, the MinIO has storage classes like Amazon, standard class, reduced redundancy class. So you can choose these erasure scheme, and application at runtime can choose, hey, this object is a temporary object, it's non-critical object. They can choose different erasure schemes at an object level granularity. And so this is basically the MinIO backend. MinIO can also sit on top of other storage systems and make them look like S3 compatible. One of the things that the important highlight here is, right, all of the meat in MinIO is inside that web server. So essentially in this mode, what we are doing is we turn off our erasure code, and then we actually have to do more work here. Like this, we started doing this work after Microsoft reached out to us, and they wanted us to add native support for Azure Blob. I'm like, we already have a lot of deployment in Azure Cloud. Look at all the data points. And they said that they knew very well that MinIO is running in Azure Cloud. And they said that's a problem, because they are running us on their file or a block share. And the data that is coming into Azure Cloud is now not readable by Azure ML or Power BI, because they don't speak S3 API. So what they said was, can you make MinIO run on top of Azure Blob? I'm like, why would I put an object storage on top of object storage? And they said that their file and block are considered legacy. It's true for all public cloud. That was a valid point. The second point they said was that data sitting on Azure Blob means you get Azure ML, Power BI, anything, they all get nicely integrated. I said, okay, it makes sense as long as we are in the data path, data is coming to us through us, so we will support that natively. Once we did that, Google wanted same thing. Then Alibaba did this on their own. There's like actually more than 24 adapters last, like 2 years before when we checked, community is maintaining a whole bunch of these adapters. We officially support like 6 or so. But why are we even doing this? It is in our interest that industry converges onto one API. The more applications they adopt, I don't necessarily like S3 API because it's not a standard, but it's okay. The winner sets the standard, right? So we enable this. And there are these features I'll just touch upon quickly. These things, they have been hardened in the enterprise environment because these were actually, we work closely with the financial institutions. They were the primary reason for the private cloud to start growing. And for them, these features, it's not like enterprise grade. They don't talk in those terms. They actually talk in terms of these are important features. Without it, we cannot go to production. And we learned a great deal working with them. We understood what it means to be modern cloud-native infrastructure. They understood what it means to be business critical. And working with them closely, so like this one, for example, it looks exactly like Amazon IAM. Even the security, like passwords, for example, most breaches happen because you saved it in a config file or some database, right? And one of your own former employees still had access and then everything is breached. Amazon Capital One breach happened because of Amazon's former employee, right? Everything you want it to be dynamic. No passwords should be static. It's negotiated, and they keep expiring and they keep renewing. So and then once the identity is established, you actually give a very restricted API level, data level control. You cannot do anything more than these operations. MinIO has a very sophisticated Amazon compatible identity management and access policy, but underneath, we can plug into your corporate identity IDP, could be Active Directory, could be like anything OpenID compatible. So this is one of those, right? So encryption, for example. Every object is independently encrypted, and on the keys, we should not control. Even if you hired me, I'm your sysadmin, right? The last thing I want is a liability for me. If somewhere something got breached, now I get pulled into that. I have access to physical drives, I have access to MinIO source code, but I shouldn't be liable for your data breach, right? The fundamental reason that customers come to us is we are now running in production. They don't want to lose data. They don't want data to be breached. And this is one of the important reasons. And the passwords are actually object level keys stored in an external key management service. And we actually put a considerable amount of effort in this. We even have another feature, a key management service that sits in front of, like, say, HashiCorp Vault or any public key management service, because the rate at which we get pounded at high performance environment, if each object, when get or put, I'm talking to a key management service will be the bottleneck. It'll, in fact, crap out within 5 minutes, right? We actually have a key management service that acts like a stateless key management proxy. And we can handle massive amount of load. All the external key management service has to do is bootstrap the system, and then it's free of it. From that to like Lambda Compute functionality, like full-blown Amazon compatible model. In fact, this is becoming more and more important because customers actually look at now object storage as the primary data sink. All the data that comes in first goes to object storage. Then they run Teradata or Presto or Spark to do schema on read. If that's the case, the data coming in, MinIO becomes the primary data source. Data is coming in, and as the data comes in, they want to be able to kickstart a Spark job, or it could be some data scanner. You want to do say OCR analysis on a check deposit, things like that. Here is where Amazon sets the Lambda Compute serverless framework, but then in the private cloud, you don't have Amazon's SNS SQS, but you have Kafka, you have NATs, like. MQTT, when initially one community guy contributed MQTT, which is IoT protocol, IoT world equivalent of AMQP. I was like, okay, let's take it. I don't know who will use it, but we actually took it. Surprisingly, we started seeing customers, like medical imaging companies, like they started using that, and they use that to actually make sure that the data came in, they are verified, and the data scanned images are correct. So we have an extensive list. These are some of the things that are important to notice. If Amazon wants to come into private cloud, they don't have these kind of abilities. Building a product and building a service are a very different game. This is where that Amazon will need MinIO to go into the enterprise.
So do you have any of those on-premises features in the upcoming demo you've got, or?
It's actually very easy to show the demo. It's not there in the demo. The actual list is even longer than this. It's quite easy.
If it's a differentiator, I thought maybe you might have into it.
Because this has been there since beginning, so we didn't, there are better things to show demos, so I didn't include. So, like this one, reason it doesn't have a pretty picture is because this got introduced only recently, literally like couple of weeks new. Amazon finally, we used to have Worm, Amazon didn't have Worm, so we added Worm because you have to have that in the enterprise space, financial space. But finally, when Amazon introduced they call it object locking. Under object locking, they have basically have retention, compliance, and governance policies. So some breach happened, you should be able to freeze the system, but not disrupt what's already running. And these are the features that where finally object storage is showing that it's better than what traditional NAS SAN systems. And MinIO has exactly Amazon compatible capability. You can even set these policies that any object that comes in, for 6 months you cannot tamper them. Or maybe upon breach you go freeze it, and then next 6 years they cannot tamper them. Like basically you can set like rich policies at even a per object level or a per bucket level or a whole cluster. And this is turning out to be a very important requirement for the enterprise.
Would you set that, you say you set that for specific buckets? You would have to then, if you start pulling that in, you might have to set up write policies to make sure that it's written to the files are written to the correct.
So so Amazon has like basically anonymous policy, then they have bucket policy. They have like many different ways to do the same thing. This is where the problem. If you see a lot of these breaches happening on Amazon, why is that the case? Amazon understands these problems well. They can easily fix it, right? Why are they not fixing it? There are too many ways to do the same thing, and then also there are too many approaches, and this is where because nobody understands these kind of mechanisms. So the policies that you asked, right? It's actually not part of this. This is only for object locking, retention. Within this, like there is compliance, retention, and governance, and there are subtle. While they look like they are similar, but they are actually there is a big difference in how they behave. And this has nothing to do with access control. In fact, Amazon deprecated access control because access control and bucket policies were doing the same thing. Then there is bucket policy, and then there is IAM policies. Bucket policy is to one. It's wrongly named. They call it bucket policy, but bucket policy is to only enable anonymous access. So I want public to be able to read without access key, secret key. Then they have pre-sign access. Then they have then they have IAM policies. That is where you actually will tell documents that this particular user or application can only perform these operations on these objects. That alone, like if I spend a whole day educating an application team, they will come out confused. So what did we do? Basically, we said, here is a simple set of tools. You don't get confused. The best way to achieve security is to actually make it simpler, right? Don't confuse them. Firewall is only as good as the user of the firewall, and giving them something simple policies is how you get it to become secure. The more easier it is, the more they will start using it. And the MC, if you see, everything is part, even ILM, lifecycle management to the policies, everything becomes part of the MinIO functionality. So this one, one is the legal log and things like that. The other one is the lifecycle management of the data itself. Say, I want these objects to be automatically deleted in 6 years. You set the policy and you forget it, and MinIO will automatically take care. Okay. I think we're done with that. There is like whole laundry list of features. We don't take pride in saying that we have more features than others. It's really what we care is these are all you need, and it's easy, and you take it to production.